Ever stop to think about the journey of the stuff around you?
Hmm.
Like, how does that bag of garden fertilizer actually come into existence? Or, what's the secret behind the gleaming surface of your favorite piece of jewelry?
The hidden life of everyday materials.
Exactly. Today, we're embarking on a fascinating deep dive into a collection of experiments that reveal the hidden chemistry powering these everyday wonders.
Right. We're talking fertilizer, plating, even like weird foams.
Yeah, from boosting your tomato plants to coating metals and even creating bubbles in unexpected ways.
That's right. And if you've ever been curious about the fundamental processes shaping the materials we use, well, every single day you're in for a treat.
Okay.
We've got a set of really illuminating experiments to explore, and our goal is to extract the core scientific concepts and those satisfying aha moments.
Those connections between just looking at something and understanding the chemistry behind it.
Exactly. Linking simple observations to the essential principles of chemistry. We're talking clear explanations and real understanding, no confusing jargon if we can help it.
Okay, let's kick things off then. First up, fertilizer.
The garden shed staple.
Right. The first experiment we're looking at is all about creating ammonium sulfate, which, as our sources highlight, is a go-to fertilizer for many.
Okay. How'd they make it?
The method was surprisingly straightforward, actually. Mixing sulfuric acid with ammonia solution.
Acid and base. Okay.
Yeah, until that telltale ammonia smell appeared and the solution hit a pH of 7 or higher.
So neutralized or maybe slightly alkaline.
Exactly. Then they evaporated the water, let it cool, and just like that, ammonium sulfate crystals.
Nice. Solid crystals.
Safety was paramount, of course. Eye protection was a must.
Makes sense. Ammonia can be irritating and sulfuric acid is definitely corrosive.
Yeah.
What's really interesting here, though, is how this simple procedure showcases a fundamental chemical interaction, an acid-base neutralization.
Right. Sulfuric acid, ammonia solution.
Sulfuric acid is a strong acid, and ammonia solution is a base. Their reaction essentially cancels out their extreme properties, forming a salt ammonium sulfate in water.
Okay, so that salt is the fertilizer.
Yep. And that final whiff of ammonia, it indicates that just enough base, maybe a tiny bit more, was added to completely neutralize the acid.
So we've made this stuff, and it's a popular fertilizer. It makes you wonder what makes ammonium sulfate such a go-to for gardeners.
Good question.
The experiment even hints at calculating its nitrogen content, suggesting that nitrogen must be pretty vital for plants.
Absolutely vital.
This simple lab work really brings home how we can chemically produce essential nutrients for the things we grow.
Absolutely. Nitrogen is a cornerstone for plant growth.
Right.
Think leafy green parts, chlorophyll production.
Photosynthesis fuel.
Exactly. Ammonium sulfate is effective because it provides nitrogen in a form that plants can readily absorb, the ammonium ion. Plus, ending up with solid crystals is a big advantage for storage and easy application.
Ah, practicalities.
The large-scale production of ammonia for fertilizers, the Haber-Bosch process, is considered one of the most significant scientific advancements ever in agriculture. It basically changed the world's food supply.
Wow. Okay, that definitely puts things in perspective. Right, shifting gears now to something with a bit more zap.
Zap. Okay, I'm intrigued.
The next experiment dives into the electrolysis of a copper-2 sulfate solution.
The classic blue solution.
Yeah, using plain old carbon electrodes. And the striking observation was the formation of shiny new copper on one of the electrodes.
Okay, so here we're seeing electrolysis in action using electrical energy to drive a chemical reaction that wouldn't happen on its own.
Right, electricity making chemistry happen.
Copper-2 sulfate in solution breaks down into ions. You get positively charged copper ions, QO, and negatively charged sulfate ions.
Okay.
The experiment points out that copper forms on one of the electrodes. Now, given that opposite charges attract.
Those positive copper ions would go to the negative electrode.
Exactly. Which scientists call the cathode.
That makes sense. So the copper went to the negative side, confirming that copper ions in the solution carry a positive charge.
Precisely.
Then, in a neat demonstration of a practical use, they actually plated a key or a keyring with copper.
Ah, electroplating.
Yeah, it makes you think about how many everyday objects get their shiny coatings this way. Jewelry, maybe parts of cars.
For sure. Chrome plating, silver plating, gold plating. It's all based on this principle. And what's clever is what they did next.
Oh.
They tried to remove the copper plating by simply reversing the electrical connections.
So that copper looks pretty stuck on that key.
Sure.
Could we actually take it off again just by flipping the switch?
That's a brilliant way to illustrate the reversibility of this electrochemical process.
How does that work?
Well, by flipping the direction of the electric current, the electrode that was the cathode, where copper was deposited, now becomes the anode, the positive electrode. So now instead of copper ions gaining electrons and becoming solid copper,
The solid copper loses electrons.
exactly, the copper atoms on its surface start to lose electrons and dissolve back into the solution as copper ions. Poof, plating gone.
That's really neat.
And this principle, using electricity to manipulate metals, isn't just for decoration. It's fundamental in refining metals to incredibly high purities.
Like purifying metals. How would that work?
Think about scrap copper. It might have other metals mixed in. If you make that impure copper the anode in an electrolytic cell with a pure copper cathode,
Okay.
as electricity flows, the copper from the impure anode dissolves, travels through the solution, and plates onto the pure cathode as very pure copper.
Leaving the impurities behind.
Mostly, yes. Either they don't dissolve or they fall to the bottom as sludge.
That's actually quite ingenious. And once again, safety first. Eye protection is crucial, right?
Definitely. Copper sulfate solution can be harmful. Okay, now let's move on to something a little more
Foamy.
foamy, like bubble bath. Kind of. Our next experiment explores how to create a stable foam using a surprising combination. Laundry detergent, aluminum sulfate, and sodium hydrogen carbonate.
Sodium hydrogen carbonate. That's baking soda, isn't it?
Good old baking soda, yes. The crucial part is observing what happens when these things get mixed together.
Okay, I'm picturing it. Laundry detergent, this aluminum stuff, baking soda. What happens?
It's like a mini eruption in a beaker. You combine these seemingly unrelated substances, and suddenly you've got this, stable, foamy concoction.
Wow. The experiment notes a similarity to the carbon dioxide production we see in baking.
Exactly. That's the key chemical insight here. When aluminum sulfate and sodium hydrogen carbonate react in water, they produce carbon dioxide gas. Lots of bubbles.
Okay, so gas is being made. Where does the detergent come in?
The laundry detergent is the foam stabilizer. Detergents contain molecules called surfactants.
Surfactants, they
Yeah.
reduce surface tension, right? Like in washing clothes.
Precisely. They help those carbon dioxide gas bubbles stay trapped in the liquid by reducing the surface tension of the water. That leads to the formation of a stable foam, not just bubbles that pop instantly.
So the secret ingredient for the foam isn't just mixing liquids, it's that gas being produced and then getting trapped by the detergent.
You got it.
The experiment also asks us to think about other foams we encounter, like shaving cream or whipped cream.
Right. And in those cases, the mechanism might be slightly different. Shaving cream often uses pressurized gas, and whipped cream involves physically whipping air into fat and protein molecules that act as stabilizers.
But the principle is similar, trapping gas in a liquid.
The underlying principle of trapping a gas within a liquid matrix to create a foam structure is very similar, yes. And isn't it surprising
What's surprising?
that laundry detergent and aluminum sulfate can create something akin to the bubbly action of baking soda and vinegar, which is a classic acid-base reaction releasing CO2?
Yeah, that is unexpected.
It really highlights how seemingly different chemicals can produce similar visible effects in this case. Gas production leading to things like foam. Safety note here. Detergent can irritate skin, so eye protection again.
Always good advice. Okay, absolutely fascinating. Now, from the light and airy world of foams to something a bit more grounded.
Grounded. Like literally from the ground.
Pretty much. The next experiment looks at extracting metals from rocks, specifically getting copper out of malachite.
Malachite. That's the green copper mineral, right? Copper carbonate, mostly.
That's the one. And this experiment feels like a step back in time, like ancient metallurgy.
It truly does. This experiment models a very basic ancient method of metal extraction called smelting.
Smelting. Okay, how do they do it?
They took crushed malachite, mixed with charcoal powder, just carbon, basically heated it intensely in a crucible, often covered with more charcoal to keep oxygen out.
Intense heat. Sparks are mentioned, so sounds dramatic.
It can be. Then after heating, they added the resulting powder to water. The final step was to separate the heavier copper from the lighter charcoal.
How? Just by swirling?
Yes, swirling and decanting. The dense copper sinks, while the lighter charcoal gets suspended in the water and can be carefully poured off.
Okay, so that intense heating with charcoal is the key chemical step. The source mentions this is a reduction reaction involving carbon. What's happening on a chemical level there?
Good question. When you heat copper carbonate, malachite, it first decomposes. It breaks down into copper oxide and carbon dioxide gas.
Okay, so copper oxide, still got oxygen.
Right. Then the carbon in the charcoal acts as a reducing agent. At high temperatures, it reacts with the copper oxide. The carbon essentially steals the oxygen atoms from the copper oxide, forming carbon monoxide or carbon dioxide gas.
And leaving behind
Pure metallic copper. That's the reduction. The copper ions in the copper oxide, which have a positive charge, gain electrons, usually indirectly from the carbon, and are converted back to elemental copper atoms with no charge.
Got it. Carbon pulls the oxygen away, freeing the copper.
Exactly. And then the swirling in water is just a clever physical separation based on density.
The experiment also touches on more modern extraction methods, right? Using sulfuric acid.
Yes, it alludes to hydrometallurgy. You can react malachite with sulfuric acid, which dissolves the copper to form a copper sulfate solution.
Ah, copper sulfate again.
And then you can use electrolysis, like we discussed earlier, to get very pure copper from that solution.
So different routes to the same metal.
Exactly. It's remarkable to see how both these ancient techniques, like smelting with carbon, and more contemporary industrial processes rely on fundamental chemical principles: reduction, solubility, electrolysis.
It really connects us to how humans have been working with the Earth's resources for millennia: safety again, eye protection, care with hot crucibles and sparks, and copper compounds can be harmful.
Always sensible. Okay, ready for a complete change of pace?
Lay it on me.
Polymerization.
Ah, plastics. This experiment shows how we can take tiny molecules of phenylethyl,
Also known as styrene.
right, styrene, take those single units, the monomers, and link them together to create long chains of polyphenylethene.
Or polystyrene, as most people know it.
Exactly. It's like building with molecular Legos, isn't it?
That's a perfect analogy. Phenylethyl is the monomer, a single building block. In this experiment, they use something called didecanoyl peroxide.
Sounds complicated.
It's just an initiator. When you heat it gently, it breaks down and starts a chain reaction. It causes the phenylethyl monomers to add to each other over and over again.
How do they link up?
The styrene molecule has a double bond between two carbon atoms. The initiator helps break one part of that double bond, allowing it to form a new single bond with the next styrene molecule, which then does the same, and so on, creating those long, repeating polystyrene chains. That's the polymer.
So they heated this mixture in a water bath. Why a water bath?
Probably for gentle, controlled heating. Polymerization reactions can sometimes get quite vigorous.
Okay. And then adding ethanol caused the solid polystyrene to precipitate out.
Right. Polystyrene isn't soluble in ethanol, so adding ethanol makes the solid polymer crash out of the solution where the reaction happened.
And seeing the resulting solid, maybe white and opaque compared to the starting liquid styrene, it really highlights how different the properties of monomers and polymers can be.
Absolutely. Monomers are often liquids or gases, relatively simple small molecules. Polymers are macromolecules, huge long chains, and they're typically solids with very different physical characteristics like hardness, flexibility, melting point.
Polystyrene, for instance, is that rigid, often brittle plastic used in packaging or disposable cups.
Exactly. This experiment provides a tangible demonstration of how these long molecular chains form and how that fundamentally changes the material's properties.
And as you said, polystyrene is incredibly common. Packaging peanuts, CD cases, insulation.
All over the place. So this experiment gives a glimpse into a really important industrial chemical process. Safety note. Styrene in the initiator can be irritants and flammable, so good ventilation or a fume hood is essential, plus eye protection. Got it. Okay, moving on. We're now going to explore cracking hydrocarbons.
Ah, breaking big molecules into smaller ones, crucial for fuel.
Precisely. This experiment models a vital industrial process where large hydrocarbon molecules, the sort you find in crude oil,
Long chains of carbon and hydrogen.
are broken down into smaller, more useful ones, such as the components of petrol or gasoline.
This is indeed a massive industrial process, essential for meeting our global energy demands. The experiment involves heating a hydrocarbon oil, maybe something like paraffin oil that's been soaked in mineral wool.
Okay, so the oil is held on the wool. Then what?
It's heated strongly and the vapor passes over a heated catalyst. In this case, the source mentions porcelain chips acting as the catalyst.
Porcelain chips, like from a broken plate.
Well, maybe purpose-made porous porcelain. But yes, the combination of high temperature and the catalytic surface helps to break those long hydrocarbon chains into shorter ones.
Does the catalyst get used up? No, that's the point of a catalyst. It speeds up the reaction without being consumed itself. Industrially, they use more sophisticated catalysts, often zeolites, to control precisely which smaller molecules are produced.
Ah, so they can target making more petrol components if needed.
Exactly, depending on market demand for petrol, kerosene, diesel, etc.
So the experiment produces gases. What did they do with them?
They collected the gaseous products, probably over water, and then tested them for various properties.
Yeah.
What they looked like, how they smelled, likely quite different from the starting oil, whether they were flammable.
Which they probably were if they're like petrol components.
Highly likely. And crucially, how they reacted with bromine water.
Bromine water. I feel like we've heard that before. Oh, wait. Wasn't that mentioned in relation to polymers or something? Testing for double bonds?
Not polymers directly, but
Hey.
yes, it's a test for unsaturation, the presence of carbon-carbon double or triple bonds.
And why is that relevant here?
Because the cracking process doesn't just make smaller alkanes, hydrocarbons with only single bonds. It often produces alkanes, which are unsaturated hydrocarbons containing at least one carbon-carbon double bond. These are also valuable chemical building blocks.
So the bromine water test checks if alkenes remain?
Exactly. Alkenes react readily with bromine water, causing the characteristic orange or brown color of the bromine to disappear. If the gas decolorizes bromine water, it confirms that cracking produced unsaturated molecules.
Fascinating. So this small-scale lab experiment really demonstrates the core principle behind refining crude oil into the fuels we use every day. Safety.
Eye protection, obviously. Care with flammable gases produced. Also, a warning about suckback, preventing water from being sucked back into the hot glass tube as it cools, which could shatter it. And bromine water itself is harmful.
Lots to be careful about there. Okay, our chemical exploration continues with metal displacement reactions.
Ah, the reactivity series in action.
This experiment investigates the reactivity of 4 metals. The sources mention zinc, magnesium, copper, and lead. It observes whether they react when placed in solutions of other metal nitrates.
It's like a chemical competition, isn't it? A league table for metals.
A chemical battle for supremacy. That's a great way to think about it.
The core idea is straightforward. A more reactive metal will displace or push out a less reactive metal from a solution of its salt.
Okay, give me an example.
Well, let's take zinc and copper nitrate solution. If zinc is more reactive than copper and you put a strip of zinc metal into the blue copper nitrate solution,
What happens?
the zinc atoms will lose electrons and become zinc ions, dissolving into the solution. At the same time, the copper ions in the solution will gain those electrons and deposit as solid metallic copper onto the surface of the zinc strip. You'd see the zinc getting coated in brown copper.
So zinc literally kicks the copper out of the solution.
That's the essence of it. The more reactive metal prefers to be ions in solution.
The experiment uses a simple spotting tile, like a little tray with wells, to observe these reactions, and a table to keep track of which metal reacts with which solution.
Right. You test each metal, say magnesium, in each of the other metal nitrate solutions, copper nitrate, lead nitrate, zinc nitrate. You record whether you see a reaction, usually a color change, on the metal strip or in the solution.
And by looking at the pattern of these reactions, who displaces whom, you can establish the order of reactivity for these metals.
Precisely. If magnesium reacts with zinc, copper, and lead solutions, it's the most reactive of the 4. If copper doesn't react with any of the other solutions, it's the least reactive. You build up the ranking.
Magnesium, then zinc, then lead, then copper, something like that.
That's the typical order for those 4, yes. This reactivity series is incredibly useful. It allows chemists to predict whether a particular reaction will occur.
Does it have practical uses too?
Absolutely. Understanding reactivity helps explain corrosion, why iron rusts when exposed to air and water, especially if less reactive metals are present. It's also key in designing batteries, which often rely on the potential difference generated by 2 metals of different reactivity. And things like sacrificial protection, where you use a more reactive metal like zinc to protect steel from rusting.
Ah, like galvanizing steel.
Exactly.
Yeah.
Okay, safety note. Eye protection needed, and some metal nitrate solutions, like lead nitrate, are toxic.
Right. Okay, now let's turn our attention to the role of temperature in chemical processes.
Heat things up, cool things down.
This experiment looks at how temperature affects the solubility of ammonium chloride in water.
Solubility, basically how much stuff can dissolve in a liquid.
Right, and this experiment explores a very common observation. Most solid substances dissolve more readily, or you can dissolve more of them in warm liquids than in cold ones.
Like sugar and tea.
Exactly. The procedure here involves dissolving a fixed amount of ammonium chloride in varying volumes of hot water.
So making solutions of different concentrations.
Yes. And then they carefully cool each solution down, observing the exact temperature at which crystals start to reappear.
Ah, the saturation point at that specific temperature.
Oh.
The crystallization temperature.
Precisely. By noting this crystallization temperature for different concentrations, which correspond to the different initial volumes of water used.
You can map out how solubility changes with temperature.
You got it. You directly see the relationship between how much of the solid can dissolve and the temperature of the solvent, the water. It's the scientific basis for why you can dissolve way more sugar in hot coffee than in iced coffee.
It provides quantitative data for that everyday observation. If you were to plot the results, solubility on the axis and temperature on the x-axis, you'd likely see a clear upward trend for ammonium chloride solubility increases as temperature increases.
And this principle isn't just for making sweet drinks, is it?
Oh, definitely not. It's crucial in many chemical processes. Think about separating mixtures or controlling reactions, and especially in purification techniques.
Like the next experiment.
Exactly. Understanding solubility and temperature is fundamental in many lab and industrial techniques, including recrystallization, safety, eye protection. Ammonium chloride is harmful.
Okay, so speaking of getting things pure, the next experiment focuses on purifying an impure solid sample. The example used is alum.
Alum, potassium aluminum sulfate, often used in pickling or as a styptic.
Right. And the technique is called recrystallization. It sounds like a way to wash away the unwanted guests in a chemical sample.
That's a perfect way to put it. Recrystallization is a standard, powerful method chemists use to obtain pure solid compounds from impure mixtures.
How does it work, step by step?
Okay, first, you dissolve the impure solid in the minimum amount of a suitable hot solvent. In this case, water was likely used for alum.
Minimum amount. Why minimal?
To make sure the solution is saturated or nearly saturated with your desired compound, alum, when it's hot. You want as much dissolved as possible, but no more solvent than necessary.
Okay. Dissolve hot. Then what?
Then, while it's still hot, you filter the solution. This removes any insoluble impurities, bits of grit, dust, anything that didn't dissolve along with the alum.
Hot filtration. Tricky.
Can be. You need to keep everything hot to prevent your desired compound from crystallizing out prematurely on the filter paper.
Okay, so you filtered it hot. Now you have a hot, clear solution, the filtrate.
Right. This filtrate hopefully contains mostly your dissolved alum, plus any impurities that were soluble in the hot solvent. Now you let this filtrate cool down slowly.
And because solubility decreases as it cools.
Exactly. As the solution cools, it becomes supersaturated with respect to the alum. The alum can no longer stay dissolved and it starts to form solid crystals.
Pure crystals.
Ideally, yes. Because the crystal lattice structure prefers to incorporate only alum molecules, the soluble impurities tend to stay behind in the cold solution. Slow cooling helps form larger, purer crystals.
And then you just collect the crystals.
Filter them off from the cold mother liquor, the remaining solution. Maybe wash them quickly with a tiny bit of ice-cold solvent to remove any surface impurities, and then let them dry. Voila, purified alum.
That's quite elegant. The source material highlights some key terms here.
Ah, yes, the vocabulary of purification.
Dissolve, solvent, filter, filtrate, evaporate. Though less so here. Solute, crystallize, crystal.
Knowing those terms is key to understanding the process. Choosing the right solvent is also critical. You want something where your compound is very soluble hot, but poorly soluble cold, and where the impurities have different solubility properties.
Makes sense. It sounds like a really fundamental technique.
It absolutely is. Recrystallization is a cornerstone in synthetic chemistry, pharmaceuticals, materials science, anywhere you need a pure, solid compound. Safety. Eye protection, care with hot apparatus.
Right. Okay, our final experiment takes us out to sea, metaphorically speaking.
Ah, the ocean. What treasures await?
Chemicals from seawater. The goal here is to separate some of the various salts that are dissolved in seawater. We all know it's salty, but it's much more than just sodium chloride, right?
Oh, absolutely. Seawater is a remarkably complex cocktail of dissolved ionic compounds. Sodium chloride is the most abundant, sure, but there's magnesium, sulfate, calcium, potassium, bromide ions, trace amounts of almost everything, really.
Wow. So this experiment tries to tease some of those apart.
It outlines a basic approach, yeah.
Yeah.
Seems to rely on differences in solubility and maybe some simple chemical reactions.
What are the steps?
It involves boiling the seawater first. This concentrates the dissolved salts as water evaporates.
Okay. Makes it saltier.
Right. Eventually, some salts might start to precipitate out as the solution becomes saturated. The experiment mentions decanting the remaining liquid, pouring it off to separate it from any solid residue that formed.
So maybe the least soluble salts come out first.
Potentially, yes. Different salts have different solubilities, and those solubilities also change differently with temperature. Then it mentions testing the solid residue with hydrochloric acid.
Why acid?
That's likely a test for carbonates. If carbonates like calcium carbonate, from shells, etc., were present and precipitated, they'd react with the acid to produce carbon dioxide gas, fizzing.
Ah, okay. Like the foam experiment precursor.
Sort of, yeah. Then there's more boiling of the decanted liquid, likely to concentrate it further and perhaps precipitate out more soluble salts, followed by filtration to collect the final solid residue.
So by observing what happens at each stage, what precipitates when, what reacts with acid, we can start to get a sense of the different chemicals making up seawater.
Exactly. This experiment, although quite simple, beautifully demonstrates that seawater isn't a single substance, but a complex mixture. The different salts present have varying solubilities and reactivities, which allows for their partial separation using relatively simple techniques like boiling and filtration.
It's like chemical detective work on ocean water.
In a way, yes. It gives us a tiny glimpse into the vast chemical resources contained within our oceans. Scientists are constantly exploring ways to extract valuable materials, like magnesium or even lithium, from seawater more efficiently. Safety, eye protection, care with hot stuff.
Understood. Wow, what an incredible journey through the world of chemistry today.
It really has been quite a tour.
We've seen how fertilizer is made, essentially an acid-based reaction giving us plant food.
We saw electroplating work its magic, coating things with metal using electricity.
And the surprising science behind foams needing gas and a stabilizer like detergent.
Don't forget the ancient art of extracting metals from rocks using carbon reduction.
Right, and building plastics, those long polymer chains from tiny monomers.
Plus cracking big hydrocarbons into useful fuels.
The competitive nature of metals in the reactivity series.
And the delicate dance of solubility with temperature.
The elegance of purification by recrystallization.
And finally, dipping our toes into the chemical treasure trove that is seawater. Precisely. And what's so powerful, I think, is that each of these experiments, though they might seem simple in a lab setting, unveils fundamental chemical principles.
Principles that are absolutely foundational to our modern world.
Exactly. From the food we grow, to the materials that build our homes and tech, to the energy we use. A basic understanding of these processes gives us a much deeper appreciation for the often invisible science that constantly shapes our lives.
So maybe the challenge for you listening is this. As you go about your day, take a closer look. Look at the everyday materials and processes you encounter. What hidden chemistry might be at play? What other deep dives could we take to uncover the science behind the seemingly ordinary?
Perhaps your next aha moment is just around the corner, waiting to be discovered in the kitchen or the garden, or even just looking at the sea.
A great thought to end on.